Today, we're going to be talking about real time customer facing analytics, talk about some of the pain points, some strategies to remediate these customer facing analytics issues, and we'll discuss where we come in at Solar Data and the StarRocks open source project. So, without further ado, I will jump right in. So, in terms of the agenda, we're going to discuss, as I mentioned, customer facing analytics, some of their challenges. So, things like latency, freshness, consistency, predictability, under a variety of data velocities. We're going to discuss some of the technologies that address these challenges. I'll throw a case study in. We'll look a little bit into the present day, kind of the subsequent state of analytics, open formats, lakehouse, and I'll finish off with some of the design patterns that are helping industry leaders succeed and future-proof their data architectures. Before I go, really too individual, I just want to introduce myself a little bit as well. Um, I spend most of my time educating and empowering developers within the StarRocks and Lakehouse ecosystem. StarRocks being the open source project that Solar Data is the prime contributor of. Previously worked in financial services as a data engineer, primarily working on fixed income markets. So things like data streaming, lots of time series databases, and for those familiar, various fixed income venues, and working a lot with Bloomberg. So lots of previous financial services experience. Bring that experience to the database world. So first, I kind of want to talk about customer-facing analytics, what it is, what are some of the requirements, and what are some of the challenges, because the term itself gets conflated sometimes, and people are often a little bit confused. So really, just to define it broadly, the simplest definition would be that customer-facing analytics is where you, your company, or organization, or team of engineers want to directly serve analytics to your end users. So the first place where we see customer analytics pop up a lot is things like ad tech, martech, CRM adjacent platforms. So think like products like Google Ads, Pinterest Ads, Shopify, HubSpot, Salesforce. This is where software kind of allows you to view real-time data about your, whether that be ad campaigns, customer data, engagement patterns, revenue, sales metrics, all sorts of stuff. But really, you as the end user are viewing real-time data about these things. Another spot where it shows up a lot is fraud detection. So you see things like products emerging on the market, like Stripe Radar, Sift Count, where seeing financial services fraud is super, super important. You kind of have to react as that fraud is occurring. You can't react minutes later after some transaction has happened, because at that point, money is left. Money's left somebody's account, or there's been some fraudulent transaction elsewhere. So this is also a big spot where customer-facing analytics shines. And really, more broadly speaking, any external-facing dashboard or application across a slew of industries. So that could be e-commerce, transportation, food delivery, lodging, that sort of thing. If I'm ordering, like an Uber from SFO, for example, or LaGuardia, I want to know the drivers near me at that moment, right? And the chances are that there's some back end being hit to find those drivers. I need to find those drivers as soon as possible. Could be an example with like brokerages, say Fidelity. If your portfolio is down like 20%, you want to see that in real time, not 10 minutes later. So you kind of get the idea. Customer facing analytics, or CFA, if I use that acronym throughout this whole presentation, is high stakes. It could be the revenue driver of your organization. So kind of no matter the industry, as we can see, or the industry vertical, I want my data to be fast, I want it to be fresh, and I want it to be consistent. So it sounds kind of easy in practice, in theory, as these various services, give you great SLAs. But behind the scenes, there's a whole lot of stuff going on, in that it can be a challenging kind of reality to really implement. So I'm going to start off by kind of presenting the first challenge, which we see a lot of folks facing, which I'll call Exhibit A, the denormalization challenge within customer-facing analytics. So starting off, we kind of have to be practical. A lot of our data these days is inherently relational, majority of the time. Um, and a lot of legacy, OLAP solutions don't kind of make the cut for relational data. They either don't support joins, only allow single node joins, and don't even use a distributed architecture, or have joins so expensive that they're unusable. And kind of to top it off, a lot also don't have any query optimizers or cost-based optimizers working with, maybe in some cases, more archaic rule-based optimizers that don't let you assess costs on the fly. So this is definitely a big challenge that the users face: denormalization, disk explosion. And what goes along with this is what I like to call the denormalization tax, because the result of that is that users end up having to denormalize everything and pre-compute it. The first kind of issue there is that your data pipeline is more complicated to maintain, update. You might use something like Spark to flatten and sync your data sources, and then you have all these wide tables sitting with you in production that are unruly, right? And what do you get kind of with those wide denormalized tables? Well, one is that you get immense data lock-in. So now you're stuck with these, disgusting tables that are hard to modify with a single provider. Uh, Kind of on in the same vein, you get a lot of backfilling issues. Backfilling is pretty common. Maybe there was some job that failed in between, or some junior dev accidentally exposed sensitive user information. PII breaches are very, very common these days. So you have to go through these thick tables row by row and compute, result in compute heavy operations to kind of change your data. So that's another issue with denormalized data. And the fourth, which I kind of mentioned, is storage explosion. So duplicated fields inflate your storage in some cases. We've seen with customers up to 10 times. So denormalization is definitely, despite what people might try to tell you, it's a big operational tax that you pay with tech debt that accrues and gets accrued as time goes on and only compounds as your data velocity changes. Another exhibit of challenges is, achieving query resilience and latency and concurrency under the strict SLAs that we have today. So in 2025, we have companies that are dealing with almost impossible service level agreements. So low latency under peak loads, high concurrency, thousands or in some cases millions of concurrent users. Use this as an example. When you're going on Google and I search for the weather in my location, I expect a response within milliseconds. If that takes more than a few seconds, I'm asking, well, what's wrong with my internet service provider today? That's just one small example, or using the same Uber example. If I'm looking for drivers, I expect to find a driver if I'm in some high volume, high foot traffic location within a minute or so. Usually. So it's getting the scale is increasing very, very rapidly. You have unpredictable query patterns, and all that with minimal downtime and performance delays. And then because of that, a lot of companies already have legacy architectures, and those legacy architectures bring in a lot of technical obstacles. So workplace changes, or workload changes, fragile query planners, infrastructure failures. You may not have the right disaster recovery system set up. You may have resource contention for compute in an undistributed environment or distributed. You may not have a cache in some of your query engines or query systems. And then, when you get that poor end user experience, you breach your SLAs, you get higher infrastructure costs, and a lot of the engineering teams are stuck firefighting instead of building. So I've kind of been rambling a lot about the problems for the last 8 minutes. Trust me, it's just not about, I'm not just going to be talking about problems. Um, I want to kind of introduce a solution that we provide that we think, having been with a numerous amount of clients, that we think remediates a lot of these issues. And that is the Starox open source project and the Starox OLAP database. So where does kind of Starox fit into this whole thing? Well, we provide those real-time customer-facing analytics, promising sub-second queries designed to meet your SLAs. So you could say goodbye to a lot of those pesky denormalization pipelines, say yes to mutable data directly on columnar storage. So you're able to use these normalized joins again. You don't have to denormalize a lot of your data, get that disk explosion, have a fragile data pipeline. And on the right hand side here, I kind of have a view of the architecture of Starbucks. It's very simple. You have these front end nodes that are mostly responsible for metadata and query planning, and compute nodes which execute those queries. Uh, and it can sit all on cloud object storage. And once we kind of have the integration with cloud object storage, we kind of get the notion of a lakehouse because in and of itself, we support things like Parquet, CSV, JSON, and table formats that are open like Iceberg, Hootie, Delta Lake. So you get all that performance, but you can also query the lakehouse that you already have. So you don't have to reinvent the wheel. Massively parallel, inherently based off of his architecture. C++ SIMD optimized, so we're leveraging the latest CPU architectures to execute in a columnar fashion. And we have a pretty big caching framework. So really, you're getting that data performance on the lake house. So with that being said, what are some of the strategies that we actually use to make those joins fast that I was mentioning? I said a lot about denormalization. You don't need to denormalize with Starox. How do we actually go about it? Well, first things first, we go for a modern compute architecture. So it's important to realize that a lot of architectures tailor to different uh, use cases, different purposes. So we first started with the scatter gather, right? So this would take your query, break it up into tasks, reassemble your request, the gathering part to complete the query. Now, this used to be really good for simple workloads like lookups. But what would often happen is we'd get stuck at that gathering phase as you're dealing with hundreds or billions of rows, making it not really that suitable for joins or more complex aggregations at scale. So, good examples of scatter gather are things like Elasticsearch and some earlier forms of Druid. Those are the things that come to my mind immediately on query engines that utilize this architecture pretty extensively. And then we had MapReduce, right? So this is kind of famous from the Hadoop and early data lakes. So you take your input, split it up into pieces, kind of map those pieces to executors or blocks in the compute engine, combine it, and then reduce it, right? That was kind of the map reduce part. Pretty good for large data sets, long running ETL jobs, that sort of thing, but really slow. It was kind of designed like for, okay, I have a really big blob of data. I don't really care how long it takes because one, it doesn't scale well, but it gets the job done, but it's not good for customer facing analytics. So slow for dashboards or any like real time component where you really need to be time sensitive. And when you get, now in 2025, having big architectural leaps in technologies like Starox that can leverage massively parallel architecture. So this allows subtasks rather than, conversely in the scatter gather architecture where there's one node relying on this aggregation of tasks. In the massively parallel situation, a lot of these tasks can talk to each other rather than having to wait. So this allows us to get into a situation where we have a query engine that's suitable for joins, for aggregations, and intense queries as you scale. So you don't fall into the headaches of MapReduce and you don't get stuck at that single bottleneck with scattergat. This is just one part of the equation, right? Uh, Second thing we take pride in is query planning. So a query planner that actually works. It's more specifically a cost-based optimizer. So that's kind of the next leap in what gets our performance up. So with searching or querying a database, uh, as your query changes, especially as it grows and gets more complicated, the number of ways it can be, the number of ways that it can be uh, joined, it grows exponentially. So if I have 3, 4 tables, at a certain point I'm joining more than that. There's a bunch of different combinations. It becomes kind of a combinatorial problem of how I can order all these joins. So not only do you have to consider the join order, but you have to think of different join algorithms, execution strategies. Am I going to be using hash join? Am I going to be using something like a merge? How am I going to actually be leveraging that under the hood? So that makes the search space super, super massive. So we tackle that by using a cost-based optimizer that utilizes statistics. So things like min max values, null rates, number of rows, and that allows us to estimate the cost of each query. So that uses under the hood a greedy algorithm, and that can once we've defined all these different plans, we can choose the one that costs the least. So for those who are really involved in query optimization in the audience, we develop our query optimizer from the foundations of the Cascades framework and the Columbia framework as well. So we combine that with some additional bells and whistles, and that's how we kind of created our cost-based optimizer. Something else that kind of is closely tied to our optimization is the notion of global runtime filtering. So that kind of allows us to prune like unnecessary data. So, for example, if I have a really large fact table and a smaller dimension table with, say, like a filter, a naive execution may scan the largest fact table, but in our case, we can push down a lot of those filter conditions and only have to scan the smaller table and then spread the larger table across different nodes. And that significantly reduces a lot of the CPU load. So that's kind of where our cost-based optimizer comes in. And a lot of those performance benefits, I have to be honest, they're originally they weren't always the level or standard they are now, but we were able to get there because Starrocks is open source from continuous integration and valuable, community feedback. So lots of people contributing, lots of different companies contributing to the CBO that's kind of allowed it to get to the place where it is now. And then, lastly, effective query execution. So ideally in the form of native C++ operations that talk to the machine without uh, you know, uh, any additional compilation. So things like no JVM, no bytecode. We're not converting anything. That kind of allows Starrocks to process multiple data points just with one instruction. More specifically, we rely on AVX2 instruction sets. So for those familiar, that would just be an extension of x86 default instruction sets. And with the extension, we're able to operate in a columnar fashion. So given our storage model and data processing is done in vectors, it just kind of makes sense for us to compute in vectors. That's really all that this x86 instruction set extension is doing for us. And that's where we see a massive performance gain from just the implementation language. I've been talking a lot about performance gains, but I haven't really showed any data yet. So, I have to say the motivation behind building Starrocks was really creating a system that excels at joins. And so here we can kind of see where you're able to eliminate a lot of denormalization. So this is the star schema benchmark. To preface this, I have to say the star schema benchmark has two variants, one that's usually multi-table or normalized, and a denormalized flat version that's traditionally used a lot by the ClickHouse community. And a lot of engines perform usually better on the flat version because there's kind of a lack of joins. But in this case, as you can see, Starrocks kind of stands out by not only being one of the fastest overall, but also showing that its performance on the multi-table star schema benchmark is nearly as fast as ClickHouse on the flat version, and even faster than Druid on flat, miles ahead of some of the other competitors in this graph. So that kind of shows you that you can denormalize at scale or sorry, normalize your data at scale and kind of leave denormalization behind. And even in more demanding benchmarks, which I haven't shown here, like TPCDS, especially the 1 terabyte, we outperform Trino by over 5x. So that, I think this chart I really like because it shows strengths kind of in the market, but it also kind of shows kind of puts you know facts to a lot of the denormalization stuff I was talking about earlier. I want to go in with a case study, an example here. So Demandbase, we've worked with them extensively over the last couple of years. They're an account-based go-to-market platform for B2B enterprises. And they were powering a lot of their workloads with another popular product on the market. But they kept running into a lot of the usual suspects that I mentioned before. So their data was locked in a single view. So something like a wide table And that made them waste a bunch of money and time on disk, and created a bunch of overhead. So, a lot of the real time analytics because of this became impractical. Like a lot of their dashboards were hanging, data wasn't loading. So it wasn't feasible if they wanted to remain competitive with other uh, people in the space in the B2B go to market, industry. So they came to us and they kind of revolutionized the way they started working with their real time analytics. So they migrated to Seller Data, powered by StarRox, the managed service that sits over StarRox, and ditched a lot of their denormalization. So one, they avoided a lot of storage and compute bloat. They were able to normalize a lot of their data. And considering that they were interested in going in the lakehouse fashion, they were able to simplify their architecture a lot. So on one hand, you could see here they have an Iceberg data lake that connects to a REST catalog. Uh, their front end customer facing dashboards can talk directly to their data lake with external catalog support built in StarRox. But then, behind the scenes, upstream, before the ETL jobs, before the Spark cleansing, their customer operations can still resume. So they can still talk to your old TB databases. You don't need to go crazy and denormalize a lot of your data here. So I like this example because it kind of shows the both sides of the equation. Your customer facing, but also your customer operations. You may have some other in-house back office business intelligence use cases that can resume as normal. Last couple slides here just to finish off. In terms of like meeting low latency SLAs, how do we look at what are some patterns that we take at StarRox, but also industry wise that you can use to kind of succeed or look for when you're looking at an engine. First thing is you want to start with a reliable cache. So with a reliable cache, you need things like proactive cache warmup. This is something we do. So filling the cache with frequently accessed data to eliminate a lot of cold start performance issues, keeping it fresh, uh, having replicas for a lot of your compute nodes. So not getting into the trap of just having one cluster. We have a lot of clients that actually only operate with a cluster or two just because how performant StarRox is, but still a good idea to have region failover or replica or in-sync replica when something does happen in case something happens. And the last thing is we use the concept of a segmented LRU. So uh, what happens with some traditional cache implementations is a lot of the cache can get polluted and kind of wiped with one really large query. We protect the cache, so having one section that's allocated for an eviction and one that's protected just based off of your querying patterns. So the entire cache doesn't get flushed out. So we take pride in the way that we implement our cache. And the second thing is just kind of in general ensuring lower latency on your data lakes. So statistics collection, we gather statistics directly from Iceberg. So that in general just leads to better query planning. Um, we use global dictionaries, low cardinality dictionaries, and bitmap indices. So that kind of allows you to map a lot of the lower cardinality tables um, to encoded dictionaries that allow you to retrieve, um, say, a field that isn't showing up too often in a column, so you don't have to keep repeating the same entry over and over again. So that allows you to compress a lot of common values, reduces memory footprint, and just being smart with your primary key and foreign key constraints. So we have the notion of primary key tables, duplicate T tables, various table formats that allow for flexibility in your data modeling. So we want data modeling freedom, but we also want some rules in how we define the table. So our cost-based optimizer can effectively prune our query. And the last one, just being smart with the metadata. So we fetch the metadata from your data lake in a distributed fashion. We also cache a lot of this metadata, so you don't have to go over the network to S3 or whatever your lake backing is, and that allows us to reduce a lot of bottlenecks by distributing and caching metadata within Iceberg and across other open table formats. Last slide here, just talking about some customer-facing analytics success stories. So I mentioned Demandbase. They were able to save over 90% on storage. simplified their pipeline a lot, and their ability to do real-time analytics. Herdwatch, another SaaS dashboard for farming, actually allowed them to bring down their Athena-based querying system from 2 to 5 minutes all the way down to 700 milliseconds. And then another client we were able to get from BigQuery to Lakehouse, and in that case, they were building a petabyte scale data analytics platform with lots of joins and normalized pipelines as well. So that is pretty much it for the presentation. That's what I had for you guys. Feel free to join the Slack or visit sellerdata.com for the managed Starrock solution. I encourage you, to join both of these, check them out.